So the chapter ends with synthesis strategies. As we go along, each of the chapters is going to end with synthesis strategies, and the strategies will become more and more complex as you know more and more reactions. Right now we know 3 different reactions. A substitution reaction converts one group to another. An elimination reaction will convert an alkyl halide to an alkene. So you're looking at something that has a chlorine, and we're going to react it, and it's going to make a double bond. An addition reaction is going to remove the double bond and it will be adding 2 groups. So this is something that we're going to need to be able to do if we're going to take this alkene and add this. We're adding water, so this is a hydration, and it's added anti-Markovnikov. So an acid catalyzed hydration would have put the hydroxy here. So this must be the borotrihydride, followed by peroxide and sodium hydroxide. Those are the reagents that you would need. So here we have an elimination reaction. We're removing the boron and we're removing a proton that's on the other side. Here I would expect, let's see, we are doing a Hofmann. This is a Hofmann because we've got the less substituted double bond. So I'm going to say that we're going to use a strong base, and it's going to be sterically hindered. So one of the T-butyl oxides would be the reagent of choice there. Here we're adding a bromine, so this is an addition reaction for C. We are adding it to this position, which is anti-Markovnikov, so we'll have to have hydrogen peroxide in the mix. Or a peroxide. It doesn't have to be hydrogen peroxide. It could be any peroxide. And here we're going to add 2 hydrogens. So let's just add hydrogen gas with the catalyst. Now, in some of these, there's more than one right answer. You could put different things in here. Okay, so there are 2 things we're going to look at. The first is changing the position of a leaving group. So here we've got the bromine on the 2nd carbon, but maybe we want the bromine on the 3rd carbon. So the way we can do that is that we can have an elimination reaction between the 2nd and 3rd carbon. There's the 2nd, there's the 3rd. And then we can add the bromine to the 3rd carbon when we add it. Okay. This is another example. Here we have the hydroxy. It's on the main chain. We add this TS group to make it a good leaving group. Then we use a sterically inhibited strong base to give ourselves this Hofmann structure, and then we add the hydroxy in an anti-Markovnikov fashion. So by selecting the correct reagents, we can move we can change the position of a leaving group. So let's look at this first example. We have a chlorine, and it's on the second carbon. I'm just numbering them. And we would like to have it on the third carbon. So what we're going to need to do, here's our chlorine, here's our methyl group. We're going to first make an elimination reaction. And then we will do an addition. So for the elimination reaction, we want to make sure that we have a reaction that occurs between the more substituted carbons. So we want a Zaphis. So we're going to use a strong base, and you could use several strong bases. I'm going to use sodium methoxide. You could use sodium ethyl oxide, you could use sodium hydroxide even. That will give us the double bond in that position. And then we'll add hydrochloric acid, and that will give us a Markovnikov addition, which is what we want because we want it on the more substituted carbon. This next one, we're wanting to move the hydroxy from the blue carbon to the pink carbon. So to do that, we're going to perform an elimination step. So let me make sure I keep my methyl group in the right place. There we go. We'll do an elimination, and then we'll add it to the end. So here's our elimination. Up here, at the blue example, we wanted to use a strong base, and we wanted a Zaphis. On this example, we want the Hoffman form. So we'll use a sterically hindered strong base. I did leave out a step. I just noticed this hydroxy is not a good leaving group, so we'll have to treat it first with TSCl and pyridine. So that's the first step, and then this will be the second step to give us this Hoffman. And then we want to add the hydroxy, but we don't want to add it to the more substituted position here. We want to add it down here. And to do that, we'll have to do the bromotrihydride. It's the BH3, and it'll be in tetrahydrofluoran. It's two-step reaction. So the first step is that, and the second step is the sodium hydroxide. And that'll get us what we want. Okay, so time is burning. So the other thing that we'll be able to do with the reactions that we know is if we want to change the position of a double bond. If we have a double bond between carbons 2 and 3, but we would like to have that double bond between carbons 1 and 2. Okay, so we do this by adding a bromine and then a selective elimination. So we'll start with this. Okay, we're wanting to move a double bond from here to down here. So first we'll perform an addition, and we'll want the bromine to be here. After the addition, we can perform another elimination, to move the double bond where we want it to be. So this first one will be hydrogen bromide. No peroxide this time, and that puts this bromine on the more substituted position. And then we'll need a strong non-hindered base. So we don't want the Hofmann, we want the Xiphus. So we'll add, I guess people get their favorites, sodium methoxide. Okay, then we're going to move the bond from here to here. So we'll start with this compound. We will want to form an addition. Then we will do a elimination. Okay, we want this addition to be Markovnikov, so we will use hydrogen bromide with no peroxide. And then here, the second step, we'll use a strong base. And again, we want it to be non-sterically hindered because we want the Xiphus. Now, if we wanted to go back the other direction, we could add hydrogen bromide. And again, we would get this form. And then to go from here to here, we'd use a sterically hindered base. Because that would give us the Hofmann. And that is it for this chapter.